So, Herr Professor Rektor, Herr Professor Dean, Herr Professor Cervenka, faculty, students, friends and families, please accept my humble gratitude for the invitation into your extraordinary community of scholars. This is indeed a great honor. I should add too, that because I have an Italian mother-in-law, now to be officially termed Adriano is a very significant advance for me. Scholarship is a global endeavor. Science is a global endeavor. The Francis Crick Institute, where I have a research laboratory, has a motto: discovery without boundaries. International travel and collaborations are one of the most compelling rewards of academia and underline my being here today. So why have I chosen the title that I have? Living in the Square of Improbability. What even is the Square of Improbability? Well, one reason underpinning the title is its derivation from Leben im Quadrat, which is a motto for the city of Mannheim, for which we all can have affection and respect. The second and equally relevant reason is because from my personal viewpoint, Leben im Quadrat is sound, practical career advice for you, today's students and young scholars, whether your hearts are in academic science, in clinical medicine, in pharmaceutical development, or even beyond those fields. Consider this. As a biologist, one might ask whether we have even learned 1% of the fundamental things that are there to know, even 1%. And yet, apparently, our scholarship is based on building hypotheses and testing them. So what chances are there of those hypotheses being correct when our information base is so small? Imagine undertaking a criminal investigation with only 1% of the relevant facts available to you. So given this situation, de facto, how should scientific scholarship be pursued? In fact, there are many approaches, but I've chosen today to discuss with you one which I think has the greatest chance of leading to true discovery and leading to personal fulfillment, no matter which area of scholarship you choose to pursue. And that is to apply the rigor of the experimental method that is within your realm, and then to maintain intense surveillance over the data obtained, ready at any time to see the unexpected that is both real and inevitable. This is the nature of true discovery. Experiencing exactly this, Pasteur famously said that luck favors the prepared mind. But for the mind to be prepared and for the surveillance of data to be effective, it must operate within a constrained space, within a square, Leben im Quadrat. But this does not need to be as constraining as perhaps it sounds. Pascal, the renowned French mathematician and philosopher, considered that the sole cause of a person's unhappiness, you may argue that it's not the sole cause of a person's unhappiness, but he argued that the sole cause of a person's unhappiness is that they cannot be left to stay quietly in their room. In so doing, he challenged the view that we must always go to new places in order to feel and discover fresh and worthwhile things. In my view, this would indeed only be the case if we had a full understanding of what is within our own room, within our own square. Whereas in relation to biology, this is clearly not the case, and I suspect the same is true for essentially all other types of scholarship. Thus, if, as Pascal would have wanted, we are left quietly to explore our own space, many unanticipated treasures will inevitably be found, so long as our methods are rigorous enough to see them and to trust our observations. Luck favors the prepared mind. The extraordinary events of the past 2 years, which included, of course, with great distress, the cancellation of ceremonies like this for those who went before us, both here and, of course, in our own university, nonetheless included lockdowns in which people who were not free to travel discovered remarkable features of their local landscape, their own squares, that they had not noticed before, walks, buildings, wildlife. Furthermore, with time to appreciate the square in which they lived, they saw opportunities to improve it. In the United Kingdom, during 13 weeks of lockdown, 61,682 applications were made for people to extend their houses, adding 1.5 million square feet of living space to the nation. 32%, that's almost 1/3 of property owners were engaged in renovations compared to 18% before COVID. Yes, so your square can be reinvented, but it's still your square. Your square of scholarship can be revised, but it's still the square with which you can become productively identified. Permit me now to use my own experience to expand upon these views. When I was young, and that was once the case, I set my sights on becoming a university lecturer because I was attracted to spending my days in an environment of education and curiosity. Soon, I realized that one's curiosity could be pursued through research, which, as Professor Cervenka has mentioned to you, gave me the opportunity to participate in a fascinating study at the Massachusetts Institute of Technology under the direction of Professor Susumu Tonegawa. So to add a little to Professor Cervenka's introduction, when a pathogen, and of course this could, for example, be the SARS coronavirus, invades, it has to pass through body fluids to find the cells, such as those in the lung, that it will then infect. This extracellular world is protected by antibodies made by B cells that, because of the pandemic, pretty much everybody knows the existence of today. Taken together, these antibodies can recognize almost anything, billions of targets, and each is highly specific, so you can discriminate this year's seasonal flu from last year's seasonal flu. The molecular basis of this remarkable system was elucidated by Professor Tonegawa, earning him the 1987 Nobel Prize, for which he was the sole recipient. The task that we faced in 1982 at MIT related to the following. When a pathogen evades those antibody responses, it can infect a cell, which becomes an incubator for the production of absolutely enormous numbers of these pathogens, just as was experienced, unfortunately, by many COVID-19 patients. Thus, there must exist a component of the immune system that can recognize and target infected cells and destroy these incubators. That component is provided by T cells that have also become familiar everywhere. And back in the 80s, our job was to try to understand the mechanism by which they may achieve this. In part, we were successful. But in all honesty, we were beaten to the initial fundamental discovery by a group at Stanford and concurrently a group in Toronto. So, why were we so slow? Why am I here? Well, because within the square in which we were working, we had discovered something completely unexpected. Because our experimental approach was robust and operated within defined boundaries, Leben im Quadrat, we could trust that the discovery was not an artifact. In fact, again, as Professor Cervenka has indicated, we had discovered an entirely unanticipated gene that went on to identify a completely novel type of T cell that was termed the gamma delta T cell. 28 years old at the time, I found the response of the Academy to be remarkable, combining skepticism with conservatism, a point to which I shall return. This skepticism, verging on hostility, only grew as gamma delta T cells failed every test that was set for them for the recognition of infected cells, the job of T cells. But the fact that gamma delta T cells can be found in essentially every animal with a backbone, be it a fish, a mouse, or a human being, strongly suggested their critical importance. So staying within the square, my laboratory, which I had by then set up at Yale, applied new tests, eventually providing clear evidence that gamma delta T cells can suppress inflammation within tissues, such as the skin and the gut, and associated with that can protect against cancer. This was at a time, in 2001, when cancer immunology itself was still regarded with immense skepticism, verging on hostility. To convince ourselves, and of course to convince everyone else, that our observations were bona fide, we needed to discover how gamma delta T cells might achieve this. The answer, of course, lay within the square. And like many things within your square, are quite obvious if your eyes are appropriately adjusted. Consider, if you will, the German intelligence agency. I believe it goes by the name BND, if this is correct. So basically, there are two ways in which this works. You have agents who identify and track down subversive individuals, specific perpetrators, just as B cells and conventional T cells identify pathogens and stop their activity. By contrast, there are other agents who rapidly identify suspicious activity. A very good example these days would be the computer hacking of bank accounts or airline ticket systems, without any idea a priori of who has perpetrated this. And this is exactly what gamma delta T cells do. They quickly notice when things are wrong, whether that problem is caused by an infection, a virus, or equally well, a toxic chemical, or even too much sunlight. This capacity allows them to detect early changes associated with tumor development and to promote biological processes that naturally limit cancer. These were, of course, rather optimistic findings. However, if we think for a moment, this perspective on gamma delta T cells carries with it a challenge. If you're going to discern what is wrong, you must first know what is normal. And I was so delighted and touched that Professor Cervenka, in her address, mentioned our work on what we have termed normality sensing. Let's consider a metaphor. My wearing of these academic robes today is regarded as quite normal in this setting. Likewise, if there was a film being made about a university, it would seem perfectly reasonable to see me dressed like this. And dare I say it, an occasional fancy dress party, it would still be okay. But if I attempted to board an aircraft, or I was found sitting on the beach in these clothes, there would be reasonable concerns about my mental health. Gamma delta T cells have to make this distinction. They must be able to establish a frame of reference, knowing what normal tissues look like, and thereby being able rapidly to detect behavior that is meaningfully atypical. This is a posit. It requires a molecular definition, and that definition was, of course, an unexpected discovery within our square. And I will share it with you for just a few moments because it brings together the experience of many of the younger individuals in the room and some of us slightly older. Bob Tiglar, an eminent, now retired professor of dermatology, well known, in fact, to Professor Geert, a very long-standing friend of ours, joined our lab in London on a sabbatical leave in 2003. As the time approached, I could sense my team's mixed emotions. It would be a privilege to have such an experienced scholar with us, but this person was going to be competing with them for my attention. And even worse, was going to be bumbling around the laboratory, not knowing where anything was kept, not knowing how any of the machines work, and consuming everyone's time and anxiety. All of those concerns proved to be extremely appropriate when absolutely nothing that Bob and I attempted worked. We could sense the morale of the lab declining. Within our square, we soon found the answer, and it was quite remarkable. The mice that we had been shipped for our experiments had spontaneously developed a mutation. The mutation was in a gene that encodes a protein that is expressed on normal skin cells and that gives the code to the gamma delta T cells that the skin is normal and everything is fine. Thus, without this gene, the gamma delta T cell experiments had no chance of working. I should emphasize that prior to this, the identity of the gene itself was not even known. There would have been no other way to pursue this form of research without sitting carefully within the square. Strikingly, we have been able to identify now equivalent genes that tell the gamma delta T cells what normal gut looks like, and in at least one case, individuals with mutations in that gene have an inappropriate gamma delta T cell compartment in their colon and are predisposed to very severe inflammatory bowel disease with a predisposition towards cancer. The square in which we live and conduct this research remains one of basic scholarship, of focus, of robust scientific method, and of improbability, where most of our preconceptions and our hypotheses will inevitably and usefully be overturned. A distinct privilege is to share that square with bright minds, particularly students, PhD students, and medical students, who enabled my lab to get off the ground in its early days at Yale. Adam Richman, Sue Keyes, Topher Dudley, Scott Roberts, Caroline Malik, John Shires, Kerry Steele, Eric Hoffman, and William Powell, who is now Chief Developmental Officer and Executive Vice President at Pfizer, kindly bringing us the BioNTech vaccine. Here in Mannheim, Heidelberg, I have been delighted to be involved for several years in the research training grant that has been mentioned, Hallmarks of Skin Cancer, set up and most devotedly run by Professor Goethe. Under his leadership, that program displays impeccable attention to training the next generation of researchers, as I am confident is the case for the other PhD programs in this university. But to that training, let me simply summarize a few simple conclusions. You are part of a global community of scholars that has the opportunity to make genuine advances in knowledge and scholarship wherever you choose that to be. This is an enormous privilege, and you will have reached this point dependent on support and patience of friends and/or family. As you train further, you can transition from one subject to another, pursuing your curiosity here or there. But at any one time, be conscious of confining yourself and your scholarship to a focus, Leben im Quadrat, without looking over your shoulders, anxious that all real treasures lie elsewhere. Remember Pascal. Your square will inevitably be full of treasures, and the only limitation is the capacity to find them and know them when you see them. To make your discoveries, you can apply multidisciplinary approaches, biology, mathematics, chemistry, often in collaboration with others. But the most important skill set that you need to acquire is the confidence and security to live in the square of improbability, prepared for the totally unexpected that will be the most rewarding. As this happens, you will become identified with a square, establishing your own scholarly identity, sine qua non. Barbara McClintock, a 20th century geneticist, devoted her life to studying maize. Her biography was termed a feeling for the organism that she developed by focusing for decades. And within that square, she found true discoveries about gene regulation, about gene transposition, which is when genes jump from one place to another at a time when genome stability was considered sacrosanct. She describes the Academy's reaction to her work as one of puzzlement verging on hostility. Yet years later, she became the first woman to be the sole recipient of the Nobel Prize for Physiology and Medicine, and is popularly identified as the woman of the corn. Now, to moderate expectations, particularly for those in the front row, not every scholar will win the Nobel Prize. But by living within a square, each of you can enjoy the thrill of discovery, not overly anxious about skepticism verging on hostility that is built on preconceived bias rather than on fact. Leben im ihren Quadrat. Finally, you might ask, is this perspective a little indulgent? Should we not be compelled to apply our knowledge to society's needs? The problem is, what are those needs? Is cancer more important than COVID-19? Is dementia more important than cardiovascular disease? The eminent physicist Stephen Hawking, asked about the cost of the Hadron Collider, stated the need that the need to focus on applied research was overstated because humans relentlessly had a remarkable capacity to find ways to apply the most obscure results, and the most obscure results frequently provided the greatest benefit. Within our own square, Oliver Nussbaumer, an Austrian postdoctoral fellow, compelled by the capacity of gamma delta T cells to detect and attack cancers, searched for ways to grow them so that they could be better characterized. Contrary to all assumptions, he found that the key was not to touch the main receptor of these cells, and by leaving that alone, found quite extraordinarily that he could grow billions upon billions of cells, laying the foundation for the formation of gamma delta therapeutics that Professor Cervenka has mentioned, that within 5 years has gone from startup to current clinical trials using the cells in leukemia, and that was this April acquired by a multinational pharmaceutical company, laying the ground, we hope, for the cell's broad application. This is, of course, of immense interest to us and of immense joy, but that area is well beyond our square. Within our quadrat, motivation is driven by scholarship, discovery, and the training of the next generation. We are always open to new revelations, semper apertus, the creed of this university. Thank you for your attention, and thank you for welcoming me into your community.
This is quite conceivably the greatest honor that I've received professionally from an international community of scholars that exists here in Heidelberg. One pursues one's scholarship convinced that there are important and worthwhile questions to answer, but one never knows, first of all, the degree to which one will find really important answers. And even if one does, one never knows whether those will be recognized as worthwhile by the community at large. And while one doesn't do science to seek that out, it is an extraordinarily rewarding experience when that happens.